The next speaker will have Sante will talk about dynamical systems in R plus S.
Okay, so first of all, let me thank Peter, Alvaro, and the organizers to have the chance to talk here. It's always Cape Town is my second home, so always good to be able to come here and speak about physics. So today I'm going to talk about a few things, really. First, I'm going to present a new way in which one can do phase space analysis of FOR gravity, in particular R plus R squared in the little example, but I'll also try to convey some general ideas that are often misunderstood, at least in the literature that I've seen so far. Okay, well, I don't think I need to comment on this. Essentially, we want to extend GR because we don't understand the dark universe. However, the biggest problem that we have when we deal with extension of general relativity is that essentially the equation, even at the cosmological level, which is the simplest stage that we can consider, are very, very complicated. And so people look for ways to go around this difficulty and to understand a bit more about these cosmologies, rather than, for example, looking for a special exact solution, and this is based on dynamical system techniques. So dynamical systems, of course, we didn't invent them in the sense that they've been used for a very, very long time, from the 50s, and it's a normal way in which we analyze the GR cosmological equation, right? One has some equations which are an autonomous system of first-order differential equations, so it's not really a big deal. However, most of the activity, particularly in the last 10 years, it was on the formulation that first Collins, then George Ellis, John Van Dyke, Gleisel as well worked on, and many others actually, to be completely fair. This kind of approach to cosmology in GRs led an incredible amount of information. In particular, most of what we know about, for example, complicated cosmological models like homogeneous or Bianchi universe is due to dynamical system analysis. So this is a very, very powerful instrument for us that should be used in different contexts. The construction of the dynamical system approach in this vision is essentially made of 3 steps. The first one is the definition of a suitable set of variables, which are dimensionless, so we don't have scale problems in our phase space. Then, basically, we translate the cosmological equation in an autonomous system differential equation. We'll see what translation means in the next slides. And then we actually analyze the phase space of this equation. So this means that given a phase space, essentially the fixed point that one has will be particular solutions. The stability will be connected to the relation between these particular solutions and the general integral. And then from the general flow, one gets an idea of what this cosmology actually will be in a global way. This theoretically. Practically, things are a little bit more complicated. What am I going to do in the next few slides is essentially show you that there are a number of different techniques that have been proposed to look at cosmology, specifically of FOR gravity, but not only. And I will take 3 main examples. The one is a paper by 2007 by Mendola, the second is a work of 2015, and the third is really recent, July. There are some other interesting proposals that are missing. One is from Peter, his collaborator. I will not get into that here in this moment, because I only need the first 2 models to give you a bit of context to understand actually the third approach. Okay, so let's get to work. First method, the first thing that one does is to try to write the cosmological equation in a way that looks easy. And this is what you normally find in literature in terms of this. This is a very comfortable way of writing the equations, and not that scary, but they have a problem. This formulation hides what one of the main characteristics of the hypercube, right? And in fact, these equations, as they are written, are incomplete. You need to actually provide an expression for R in terms of H dot and H. When you do this, then you have the fluid equation. Otherwise, you're not writing the complete equations or motions. Okay, so in the first method, that was fast. In the first method, step one is defining your variables. So we take stuff that is very similar to the density parameters that you all know, and then we take some variables that are related to the Ricci scalar, its derivative, and a specific function that appear in the equation. For the dimensionless time, we take the usual logarithmic time, as it is called, and then, of course, one arrive to a set dynamical system, which is our step two. This system, which is squeezed here because I didn't want to waste too much slides on this, contains a lot of very interesting information. I'm not going to really comment on that. The only thing that I want you to remember is that the key point of this system is this parameter here. This parameter is what distinguishes the system for different models of f. So if you choose an f, that q will be some object. If you choose a different f, the q will be a different object. And this q, when you do the calculation, is normally written in terms of f prime and f double prime and r. So essentially, in order to have a closed system, we have to express this quantity in terms of the dynamical system equations. One can do that, noticing that two of the dynamical system variables, when put in a ratio, give you essentially a function of r only. And this means that you can invert this and obtain a value of r as a function of the two variables here. So you substitute in here, and essentially you close the system. This gives you, this opens the access to a number of different models that you can analyze in this way, and this has been done and redone many times, and also in different contexts which are not necessarily related with FOR, and so on. The other point that we have to mention is how you find the solution associated to this fixed point, which is interesting. And that can be done, basically rearrange the Rajaguru equation, so the equation for H dot here. And when you do this, then you have this kind of solutions, which are solutions, normally power solutions for your scale factor. These I here are the value of the different variables in the fixed points, right? So this is actually a number. You can see that this is integrable quite easily. Of course, these solutions are not really exact solution for your system, they're just approximations, right? Approximation in which the relative value of these objects mirror the actual relative value of the coordinate of the fixed point. Okay, so this is a very nice and a very interesting approach. However, it leaves some important points unsolved. First of all, there is this issue of inversion, right? So we need to make this inversion, which means that we have to solve an algebraic equation. And just imagine that I have f of r arctangent of r, right? Or worse, sine, hyperbolic sine, or whatever other transcendental equation. This means that I have to do something numeric, but this defies the very purpose of doing dynamical system, which is a semi-quantitative method. Also, when I do inversion, I do manage doing inversion. Maybe the inversion has not got a non-trivial domain, and this means that your dynamical system is not C1 anymore, which is a mess, and generates singularities, false fixed points. It's really not very nice. The other thing that we have forgot is that we have an equation for order 4, and the solution of these equations, even in the fixed point, to be a close approximation to these equations, should be order 4, so it should have essentially 4 integration constant. When we neglect this, essentially we set into 0 these constants, and this means that there can be hidden modes in these solutions that we don't understand. So the question is, can we do better? And yes, we can. Copying the famous ex-president of the United States. A new approach can be actually built. If you actually are clever in managing your equations. So if you rewrite, for example, your action in such a way to introduce a dimensional constant that makes the terms of R dimensionless, so that your coupling constant in F are all dimensional, are all without dimensions, essentially you save a lot of variables. You have to imagine that for each dimensional variables here, you should have a different variable. So if you have 4 coupling constant, then you have 4 additional dimensions in the phase space. This is with this trick, this thing can be actually eliminated. And then you can define some specific parameters that keep track of the higher order terms, right? These are these horrible things, but they make a little bit more sense if you use the logarithmic time. right? And this makes clear what the structure of this parameter is. When you do this, and you're so brave to do the calculations, you get to this horrible set of equation, and any person who's got a bit of sense sees this and says, okay, I'm not going to go through this, but we are desperate, so we really want to solve this equation. The fact is that when you redefine your dynamical system variables, this time with object it contains only R here, the usual omega, but also stuff that is connected with high order terms and a variable that connects with this constant R0, the system is not so bad at all, right? It's a 4 differential equation. We have these functions here, x, y, that we'll define in a minute, plus 2 constraints that are here. So these x and y are essentially connected with the function f. Much in the same way with the parameter q of method 1. However, the difference is radical here, because these guys are functions of essentially the variable r and the variable a. So you can close the system for any form of the function, without making any inversion, without introducing any singularity. So essentially any form of the function f can be treated. Okay, so yes, this was my conclusion. Right, then next we have to find the solutions, and this is also something that can be scary at the first sight, but in fact it's really easy, because we have this equation here that comes from the Rajagouri modified equation, this object, which is horrible, but is a constant. And this means that essentially you can integrate h exactly for any kind of a fixed point that you have. This does not mean that we can integrate for the scale factor in an exact way, and in fact most of the time we can't. But still, we can have a pretty good idea of how the solution goes doing a numerical integration of the solution for each. Okay, so let me give you an example of the type of fixed points that we have that justifies the shameful mess that we are making with all the calculation. So one example, actually, let me show you together. 2 examples are like this, right? So you have at very, very small time solutions which are very similar to the one that we have found in the previous method, right? But then things start to change. In particular, what happens is that you have a transition to acceleration, and then you have something that you can show numerical to be essentially a static universe. The same happens here. Only the very small time t are different. Then you have again transition to dark energy and evolution towards a static universe. But the most surprising solution is this one, which happens basically for every kind of FOR you have. And this is the paradise of every person who has worked on FOR gravity so far, because you have the sitter very close to t equals 0, then you have a change in the growth rate, so that you have accelerated expansion, and then you go to dark energy. So basically this solved the totality of our problem for cosmology, and it would be very good if this solution didn't have any other features, but the problem is that the solution has got a singularity defined time. This is a double knot. Right? This analysis shows that if you want to use FOR gravity to solve your problem in cosmology, you can, but then you have to face big creep. Right? So there is a big problem asymptotically for that. For most of the models that I analyzed, this is the final attractor. It's not a global attractor, but it's the final attractor. On the other hand, these are also dark energy solutions, right? So we could be very well here or here, right, at this point. So the fact that this is appealing because it's what we have been finding does not mean that these are not interesting points. So you see that the perspective kind of shifts nicely. So again, this is more efficient, but still we have some problems that we have to deal with. And in particular, the fact that the phase space is non-compact, which means that essentially we have a boundary of the phase space, and we don't know what happens in that boundary. There are some orbits that go to infinity. We don't know if there is a fixed point, if these orbits will bounce back, whatever kind of happens there. Also, we cannot analyze h equals 0. And this is quite interesting, not only because this is the regime in which essentially you recover something like Minkowski in terms of your analysis, but it's also because we don't know essentially what stability Einstein static universe pure has in FOR gravity. And we'll see in the next slide that this is quite important for this class of theories. Also, we cannot actually make a global analysis of the phase space. If there is some periodic orbit or some strange attractor or other feature like this which are relevant for the global dynamics but not immediately connected to the fixed point, we can actually not do this analysis in this way. So again, can we do better? Yes, we can. Method 3, I don't know how much is, am I going too fast?
12 minutes.
Yeah, 12 minutes. Ooh, that's really fast, so I can just relax. I hope you understood everything. So, in order to illustrate method 3, we understood that basically we needed a complete shift of paradigm in order to understand better the cosmologies of gravity in a global way. And so we started with a very simple example, which is essentially what people call Starobinsky model. There's an alpha here that is missing, but it's okay. It's not relevant for the dynamics anyway. In the case in which we consider also especially flat cosmology, then the equations are particularly simple. So you would say, okay, then I have to do step 1 of my dynamical system analysis, and essentially I have to define some expansion normalized variable. The answer is no, because if you define expansion normalized variable, h equals 0 would be a problem. So you have to find a different kind of variables. And after many trials, what we came out was this kind of definition of variables. So this t and this x, which are eerily like the coordinates that you take to work out Schwarzschild. So I never remember if it's in inside Kruskal, one of the two. You know stuff better than me, right? The interesting thing is the relation that we have within this, which is given by this. So essentially what we have found is a set of variables in which the phase space of this model for reservoir gravity becomes a set of 2 line cones, right? They're joined in a point here that is very special. And the flow is defined by these equations, which are not so bad in terms of dynamical analysis. So this set of equations, this set of variables is globally varied. So there is no point, there is no issue with the way in which the variables are defined, which means there are no false fixed points, there are no singularity, and everything runs pretty smoothly. In addition, see, because of the definition that we have in terms of H, we know that the upper cone will contain all the expanding cosmology, whereas the lower cone will contain all the contracting cosmologies. And so we can just, and of course they are symmetric because the equations are symmetric for time variables. So we can limit ourselves to look at this cone here, right? Also, as I said, there is this point here which represents the Minkowski space. So in fact, we can analyze the Minkowski space-time in terms of this theory, which in terms of analysis of phase space is unprecedented in F1 gravity, as far as I know, of course. Right, so in order to deal with this thing, we need some, we would like to have some more compact set of variables. We still have the infinity here, right? So in order to do that, what we're going to do, and I'm going to just compress a lot of information and mathematical passages in the next step, is to define a set of 2 variables, which are written like this. So this is an angular variable that is either equal to this or equal to that. These are the variables that I defined before, right? And then a time variable, which is defined like this, right? So essentially, this writing is a very compact way to say, I take my cone, I eliminate the apex, I make it a cylinder, so I just stretch it up, and then using polar coordinates, I open up the cylinder so that I can see only a period of the orbits here. When you do this, and we can always do this without giving us any trouble in terms of mathematics, then you can analyze the dynamics of the entire theory, the entire R+R² model with a 2-dimensional system. And the equations that you obtain are here, right? Here we have redefined time because this makes the equations a little bit complicated, right? And once you have your equations, this is a perfect template for a dynamical system analysis because it's 2-dimensional. So here you have your phase space. So this is the variable t, this is the variable theta, right? So the first thing that you notice are the classical fixed points, right? So we have fixed points here and a fixed point here. Actually, this is repeated because, of course, we are already got the cylinder, right? The first represents something that you also find in all the other models that we were considering before, which is a kind of radiation-dominated solution e to the power 1/2. Then you find an object which represents an evolution in which q is equal -1, so it's a quasi-de Sitter evolution. In fact, when you look at this orbit here, this is essentially the Starobinsky model which is at work. And now we can see all its glory. And the orbit that the Starobinsky model takes for inflation is exactly this one. Right? However, since we have done things in a mathematically more strong way, now we can say quite a lot more. In particular, we can look at a global analysis. So we can actually conclude that all orbits starts at t equals 0, and they will approach t equal 1. Remember that in t equal 1, there is that Minkowski point that we have eliminated, right? That is not here because we had to stretch things up, but it's up there, right? R is a source of one parameter set of orbits. So you have a whole bunch of orbits that come here, and you can see their dynamics. So they actually go and they join this orbit that comes out from the Sitter point, which is the actual quasi-inflationary Starobinsky model. So what you can say is that here the Sitter is not a stable object, but the orbit that leaves from the Sitter is quite stable for a large set of initial conditions. Also, the Sitter here is sourced instead of a single object, a single orbit, and is also a non-hyperbolic point because points like this have weird stability. And also we have a periodic orbit which is in t equal 1. So if you look at your cylinder, you essentially have that your orbit starts from the base and then roll up towards the top of the cylinder until they asymptotically get to that point, which means that they go to Minkowski, which is exactly what we found with model 2, right, in that solution. So things have to be consistent. You can do also numerical integration. You see that this is exactly what happens, right, in natural subscript cosmology. So this basically clears up the entire phase space of this model. And in fact, with a little bit of effort that I will not show you because it's still in preparation, but you can do the same thing for any FOR models, right? Essentially, the only thing that happens is that you perform your effective light tone in the phase space. So that's kind of trivial to do. However, there are some other interesting things that you can do with this system. Since it's perfectly regular, now you can look at the relation with the Einstein frame. In the Einstein frame, it's well known that you can do the same trick that we have done, more or less. And so I will just go quickly. For people that don't know about conformal transformation in FOR gravity, one can always define a conformal transformation like this, so that the action for FOR gravity, which is non-linear in R, becomes essentially a scalar tensor, in which the scalar field is connected with the first derivative of the function f, and the potential is like this. In our specific model, essentially you have this. So you have a potential with a negative exponential that goes here. Lots of calculations. Yeah, one thing that is really important is that, and is always often forgotten in literature, this transformation has non-trivial domain. This is going to be crucial for what I'm going to tell you later on. We are assuming that this is positive. If this is not positive, this is 0. This is a singularity for the transformation. So that's quite a caveat if you want to try to do things rigorously in a mathematical way. So we do the same steps. Let me just cut out. Essentially, I define an angular variable and a radial variable that are connected to the various derivatives and potential terms in the action. The time variable is related to the Hubble factor in the Einstein frame, and I end up with this simple pair of equations, right? As before, I can look at the phase space. Now, the phase space is bounded here, so this area is not phase space, right? And we can see that there are in fact 4 fixed points, right? 2 have q equal 2 and essentially are associated with the states in which the potential of the scalar field is 0. Then there is a PL point, which is a power law solution and represent the potential dominated solution. And then the Sitter represent the quasi-de Sitter evolution, and it's again non-hyperbolic. You can see that the structure is very similar to what we saw in the other phase space. Again, this can be done, we can do a global analysis. All orbits again starts from t equals 0 and they arrive at t equals 1 where they just roll up. and then M plus minus are repellers, and they generate a one-parameter set of curves. PL and DS both generate only one single orbit, and they both non-hyperbolic. T1, as I said, is a periodic orbit, which is the limit. Minkowski is up there, essentially, as we have done it. Okay, so since we basically understand entirely the Einstein frame, we can actually compare the two phase spaces directly. And when you do the comparison, interesting things come out. Before doing that, however, let me comment a little bit more. It's possessed. Let me comment a little bit more on the domain of the conformal transformation, right? So let me define in the Einstein frame this quantity, right? Which is essentially proportional to the function f, which is the first derivative of f. If you look at the propagation equation of this quantity, you see that this presents an invariant submanifold. And this means that in the Einstein frame, f equals 0, so f prime of r equals 0, is an invariant submanifold. You cannot cross it. That's why your phase space at this piece that was actually missing orbit can get into that. However, this is not the case in the Jordan frame. So when you look at the dynamics in the Jordan frame, you can pass through f prime of r equals 0 without having a single problem in the dynamics. And this means that this happens because the transformation that we make, which is the conformal transformation, is singular when you consider f equals 0. In this respect, then, the Jordan frame, in terms of phase space, is bigger than the Einstein frame. Remember that we're talking about vacuum here, right? And the usual lore that we hear in literature is that when we are in vacuum, the conformal frames are completely equivalent. This is not true. There is a part of the phase space of F-bar gravity which is not mapped in the Einstein frame as it should, with the same transformation. Of course, you can define different transformation for different branches, but the problem that you have is that essentially, in order to do this, here you have orbits that essentially cross the F negative, F positive things. Okay, last slide. But essentially, you cannot cross this boundary. So this is quite a difference in terms of dynamics. If you want to compare the fixed points, you find that this point and this point are exactly the same, in the sense that they give rise to the same kind of solution. And then the point R that we showed connects directly to M minus and PL. And what is left here is M plus, in which the transformation again is singular. We can understand M plus if we actually put one phase space on top of the other, like in this figure here. And you understand that all these orbits here are the one that violates the condition for F negative, F positive, right? So essentially what M plus does is to collect all these orbits that generate from the part that is not transformed, and it's a symptom, it's a false fixed point, if you want, in terms of F-bar gravity. It just stays there to represent all these orbits that make this transition. I can also show in the double cone what is the piece of the phase space that is missing, and with this I go to my conclusions. So I showed you a new method to analyze the phase space of F-bar gravity, which has a number of advantages. The technique can be easily generalized to other F-bar model. The thing that comes out for all these reasons is that the phase space analysis of this model is still a matter of research. So many people think that we have solved the problem and everything is sorted out, but that's not true. There is still a lot that we don't understand about this theory. The same method helps to understand a bit better the relation between Jordan and Einstein frame, and there is a difference in the dynamics of the Jordan and Einstein frame. The other lesson that we learned from the comparison between all the different dynamical system formulation is that we have a so-called no free lunch theorem, which is a computer science term to say that no recipe is good for everything, right? Which means that when you want to analyze a certain part of the phase space, some variables are better than the other, and you have to choose all the time. There is no universal way. Yeah, this is essentially my last point. Thank you.
Okay, do you have any questions?
Have you tried to do, to study the dynamical system by using the star tensor picture? It will be much easier.
Well, that's the entire point that I'm telling you. If you do this, then you miss a dynamical part of the...
No, but I mean, not going to the Einstein frame, but just splitting the order of the equation.
Oh, you mean defining with the effective scalar field thing? No, we have not tried that, because the idea was that since you had such a simple system, we could actually match. The original idea was to match what would happen in the two frame in this context. Well, the original idea was to have a compact phase space for f-bar gravity that would not leave out anything. But what we discovered, we were expecting to have a complete complete mapping between the two frames. But what happened is that you have this chunk that is essentially missing. It's not too bad dynamically, because if you see orbits get out of that part and go to the common part of the phase space, but still, there's physics in there that you can't see with the movement transformation. So I've not done that with the other formulation, but it would be interesting to compare. Yes.
Any more questions? Yes.
How did you close your system using cosmographic parameters? Because I thought with cosmographic parameters at some point you need to.
That's a problem in the sense that in the two first methods, the variables are chosen in such a way to be density parameter. Since we have the no free lunch theorem, in order to close the system, you have to renounce to the density parameters, right? And that's the problem that is inherent in this last approach. And there's the disadvantage of having, on a side you can treat the entire phase space, on the other choosing, for example, like you do in the other methods, initial condition based on the position of the point of the phase space is basically impossible, right? Or you have to make some very complicated transformation between your data. So this is the drawback that you have with that.
Sorry for asking that.
No, it's of course, everything has got a drawback, right? That's the kind of thing, so there's no shame in that.
So you're saying that the last method works because it's vacuum, effectively?
No, you can do also matter in principle. We have not really done that yet. We have some preliminary calculation that show that there is no actual matter fixed point, which we were discussing when you were in Lisbon. So it looks like there is no matter fixed point, which is a big problem for what happened with formalism. But we still have to look into that. So maybe we can talk about that later.
Sort of a common issue. You've got r plus r squared.
Yes.
If I do a sort of take a physics perspective, an effective field theory perspective, then the other term which would be relevant is r mu,
yes.
which does not fall into this paradigm. Right?
Well, in cosmology it does, because you can prove that in cosmological metric the contribution of r mu are basically the same apart factor.
Is that
to the
only if it's a Friedman?
Only if it's Friedman.
But you see, now if you want to use this, you say, make some statements, then you face the problem. What Tim was saying, right? Now you do this, those terms will not be equivalent anymore.
Yeah,
and
you are absolutely right.
Changes significantly.
You are absolutely right. This is a problem every time you do things as simple as spherical symmetric stuff. So there are many people that do that. I don't know if he's here, but he's working a lot on this. But this is a further approximation that you make. So you think that these terms are not relevant, and you can go even further because this is only fourth order theory, right? So you could have even other correction in terms of the effective field theory. But it's with these theories we need 10 years just to understand what was going on. So we have to take it easy.
Any more questions? I have actually.
Sure.
Your format F,
Yes.
F,
Yes.
you didn't allow to be negative.
Yes, it can be negative.
Surely it can be negative as well. So can you fill in that?
But you cannot define a global transformation that contains F positive and F negative, right? Because your metric will become 0.
Right.
So that's a singularity, right, that you're introducing. And that's the actual issue. But you can define two different transformations, one for positive, one for negative. The problem is that in the Jordan frame orbits kind of crosses. So they have this transition, and then you cannot model that. Right?
No, not with some gluing for something.
Exactly, and that's kind of complicated.
Okay. Okay, let's thank Sante again.